Good day, students. Welcome to part 3 of the AP Calculus AB multiple choice practice for 1969. We're going to be going over questions 11 to 15 in this series, okay? All right, so let's take a look at question 11. It says the point on the curve x squared plus 2y equals 0 that is nearest to the point 0, comma, negative 1/2 occurs where y is. So what we're looking for here is the uh, we're minimizing the distance. Okay, when you see the word nearest, this word right here, nearest, you're minimizing the distance. Okay, minimize. Because you can always compute the distance from any point on this graph to this point 0, comma, negative 1/2. All right, so this is an optimization problem. So what we're going to be doing is we're going to be minimizing the distance from this graph to this point. We want to look for a model that shows a relationship that basically models the distance from this curve to this point. And then we're going to minimize it, and then we can then use the extrema check to see what yields the smallest distance or the nearest distance from the graph to the point. Okay? All right, so let's start by doing a real quick review on coordinate geometry. Remember, if you're looking for the length between 2 points, let's say you have points uh, x1, y1, and x2, y2. Do you remember how to compute the distance? You use Pythagorean theorem, right? So basically, the square of the distance, L squared, is equal to um, x2 minus x1 squared plus y2 minus y1 squared. Okay? This is basically the Pythagorean theorem. It says a squared plus b squared equals c squared. The length is basically the hypotenuse. Okay, so you have a point here and a point here. This is x2, y2, and this point right here is x1, y1, x1, y1. Then that distance from here to here is basically L. All right, and they have Pythagorean theorem. Basically, this is y2 minus y1, and then this is x2 minus x1. Anyway, so basically that's where this formula comes from. You might remember it. So there you have it. Okay. So what I'm going to do is I'm going to express this graph, this function right here, as a coordinate where we can pick any arbitrary point and define it as an x and y. And then I will compute the distance from any arbitrary point on this curve to this point right here. Okay, so let's start with this function. We have x squared, let me change the color. We have x squared plus 2y equals 0. So let's get y by itself. So I'll subtract x squared from both sides. We have 2y equals negative x squared. And then divide both sides by 2, you have y equals negative x squared over 2. So any point on the curve, any point on the curve can be defined by the point x for the x coordinate and for the y, negative x squared over 2. Okay, so if you pick any point on this curve, this would define what the coordinates are. All right, so now what we're going to do, we're going to let L be the distance between the 2 points. Okay, distance between, let's call the first point x1, y1, 0, and negative 1/2. This was the point we were given in the problem. Okay, we computed the distance from this point to this curve. So let L be the distance between this point, 0, negative 1/2, and any point on the line, x comma negative x squared over 2. All right. So now we're going to use a formula, but let me indicate what my variables, what each term means first. So this is x1, y1, and then this is x2, y2. All right, so I'm going to use this formula I just showed you to show you how these two quantities are related to the distance. Okay, so we're going to have using that formula L squared, which is the distance square, L squared equals x2 minus x1 is going to be x minus 0 square, okay, plus y2 minus y1, which is negative x squared over 2 minus negative 1/2, we just make it plus, right? Plus 1/2 square, like that. Okay, now this is the model that really that shows the distance between any point on this curve, on the curve we had earlier, and on this point. Okay, so remember what the goal was. We wanted to minimize it, right? We want to minimize this model. So what I'm going to do, I'm going to differentiate this implicitly and look for the critical values. Then I'm going to see where we have a sign change in the first derivative. Okay. All right. So let's go ahead and differentiate this first. Differentiate that. Okay, so we have, so derivative of L squared is going to be 2L dl dx equals, then we can use the chain rule here, differentiate this. This is going to be 2 times x. X minus 0 is just x, right? 2 times x, and then if you differentiate the inner, it's just times 1. And then if you differentiate 0, it's a constant, so that goes away. Plus, now using the chain rule here again, 2 times negative x squared over 2 plus 1 half. And then 2 minus 1 is just 1. We didn't do that there, but yeah, you have a 1 here, and you also have a 1 here. And then using the chain rule, differentiate the inner. If you differentiate this, this is basically going to become negative 2x over 2. And then if you differentiate 1 half, it's going to be plus 0. All right? So there goes the chain rule. All right, let's simplify this a little bit more. So we have 2L, the L dx, okay, equals 2x plus, now we can distribute this 2 to these two quantities in here, right here, okay? Since they both have the 2's, we just cancel them out. So it's going to be times negative x squared plus, plus 1. All right, and then this 2 divides out, so it's going to be times negative x. All right, let's just distribute this negative x to these two terms here. So we're going to have 2L dl dx equals 2x. And if I distribute that to that, we have plus x cubed minus x. Okay? So I want to minimize, I want to find where the derivative changes. So let's isolate the derivative, okay? So to do that, we got to get dl dx by itself. So basically divide both sides by 2L, right? Divide both sides by 2L. And then we're going to have dl dx equals, and if you combine these two together, it's just x equals x to the third plus x over 2L. Okay? Remember, at any point, this L is constant, right? This L is the length. So now, so we want to find a critical point so we can do a test. So to do that, we basically set the derivative to 0, right? So this is the derivative right here. We're going to set it to 0. So we have x to the third plus x over 2L equals 0. Okay? Remember, when you're finding the extrema, we're looking for changes in the first derivative. All right? So multiply both sides by 2L. You have x to the third plus x equals 0. Then you can factor out x, and then we're left with x squared plus 1 equals 0. All right? Now, using the zero product property, we can find where the critical values are. Okay? So we're going to have x equals 0. That's one of them. And then we have x squared plus 1 equals 0. Let's solve this. We have x squared equals negative 1. If you root both sides, you have x equals plus or minus I. This is imaginary, so it doesn't really count. We're focusing on the real critical values here. So our critical value is basically x equals 0. Okay. All right, so we have to make sure that we know that this is an extrema. We don't know if it's a max or min. So we can either use the second derivative check, or we can just use an interval test to do this one. Okay, so let me use the interval system to do this. There are two ways of doing it. If you want to do the second derivative, if it's concave up, then you know that that it's a minimum. Okay. All right, so let's do a interval test for this. So here goes my interval. The critical value is at 0. Okay. Now I'm going to test a number to the left of 0, x equals negative 1. And then to the right, I'm going to test x equals 1. Okay? So if I plug in negative 1 into this model, into this function right here, what happens? What is the L dx at x equals negative 1? Let's plug it in. That's going to give us negative 1 to the third plus negative 1 over 2L. Remember, the length is always positive, right? So that doesn't really count. So if you work this out, you're going to have negative 1 minus 1 over 2L, which is basically negative 2 over 2L. So what I care about is the sign. We can see that on this interval to the left side, it's negative. The derivative is negative. All right, what does that mean? That means that if the derivative is negative, that means that the function is increasing. I'm sorry, function is decreasing. Okay, so it's decreasing on this interval. All right, now how about let's do the second test. The derivative at x equals 1. Okay, so what is the value of the L dx, this derivative, on the right side of the critical value, which is x equals 1? So that's basically going to be 1 to the third plus 1 over 2L, which is equal to 2 over 2L. We can see that this is positive since lengths are always positive. So on this side, on the right side of the critical point, we have a positive slope, which basically means that on this interval, the function is increasing. Okay? So the function changes from decreasing to increasing. What happens at the critical point? That is a minimum. Okay, this is a minimum right here. Because the function was going down before, and all of a sudden it starts going up, so you have a minimum right there. Okay? So we have, let's write this down. We have a minimum. We have a min at x equals 0. All right, but what did the question ask for though? The question says, of course, where y is, so we have to be careful. We need to actually input x equals 0 into the function and see what y value that yields. All right, so let's see. The original function was x squared plus 2y equals 0. So if we plug in 0 for x, what is the y coordinate going to be? We could have used the coordinate that I generated earlier. That would be quicker, but let's just use this. So we're going to put in 0 here. We have 0 squared plus 2y equals 0. We can clearly see that here y is equal to 0. Okay? So this is where you have the minimum distance between the curve and the point 0, comma negative 1.5. Okay? So the answer is option letter B. All right, let's take a look at question number 12. So the question says, if f of x is 4 over x minus 1 and g of x is 2x, then the solution set of f of g of x is equal to g of f of x is. So basically we're supposed to set up two equations, equate them to each other, and find out what x value causes that equation to be true. All right, so this is a check on your ability to find the composition of functions or to compose functions. So what on earth does f of g of x mean? F of g of x just simply means that you are going to take g and plug it into f, right? You substitute the value of the function of g of x into the x's. So you see this 2x right here? This will go into this x position. That will be f of g of x. What on earth does g of f of x mean? It just simply means that you're going to take f, the function f, and plug it into the x in g of x. So you see this entire function right here? You take it and plug it into the x right there. Okay? So that's basically how you find the composite of functions. Okay? All right, so I guess you went over this in pre-calc. All right, now let's go over the first one. F of, let me color code it for you so you can keep up with what I'm doing. F of g of x. So you can see that in this situation, the input function is g. It gets plugged into the variable in f. So f of g of x is going to be 4 over, so anywhere you have x in the function, f of x, you substitute g of x in it. Okay? So instead of x minus 1, we'll have 2x minus 1. All right, so that's how you compose functions. All right, so let's simplify this as much as we can. So this is 4 over 2x minus 1. All right, now how about the reverse composition? What is g of f of x. What is that? Well, what we'll do here is wherever we have x in g of x, we're going to replace it with the entire function f of x, okay? All right, so let's do that. So we're going to have 2, so instead of x is going to be 2 times um, f of x, which is 4 over x minus 1, okay? All right, so to do this, we can put the 2 under here, put a 1 under the 2, and just distribute the 2 in there. So we're going to have 8 over x minus 1. All right, so what value will make these two expressions equal to each other? Well, all we just simply do is set f of g of x equal to g of f of x and solve. Okay, that's what we're going to do. So let's go ahead and do that. So we're going to have 4 over 2x minus 1 equals 8 over x minus 1. All right, so we can just cross multiply here. If we cross multiply, we're going to have 4 times x minus 1 equals 8 times 2x minus 1. All right, let's go ahead and simplify that. We can divide both sides by 4. Okay, so divide both sides by 4. And that leaves us with x minus 1 equals 2 times 2x minus 1. And then we can just distribute the 2 to these two terms right here. So we're going to have x minus 1 equals 4x minus 2. All right, so we can subtract x from both sides and add 2 to both sides. If we do that, subtract x from both sides. Let me show you what I'm doing. So I'm going to minus x and add 2. Okay, so we're going to have 1 equals 3x. So divide both sides by 3, x equals 1/3. All right, so this is the value that makes f of g of x equal to g of f of x. So our answer is option A. Okay, let's move on to the next question. Question number 13. It says the region bounded by the x-axis and the part of the graph of y equals cosine x between negative pi over 2 and pi over 2 is separated into two regions by the line x equals k. If the area of the region for negative pi over 2 less than or equal to x less than or equal to k is 3 times the area of the region for k less than or equal to x less than or equal to pi over 2, then k is what? Alright, so how can we partition that area in such a way that the region on the left has 3 times the area of the region on the right? Okay, so let me make a sketch of the situation real quick. We all remember what the cosine graph looks like from trig and pre-calc. I just want to focus on the area between um, negative pi over 2 and pi over 2. Okay, so we know that the cosine is like a cup, so it goes something like this. Let me sketch it as best as I can. Like this, and then something like that. It's kind of symmetric, right? Well, it is in fact symmetric. So there goes the region, all right? We know that these two areas are congruent, right? Because the cosine function is an even function, symmetrical along y equals x. So we want to partition it in such a way that the area to the left side is 3 times the area to the right. So that means that we have to take draw our line y equals x on to the right. Okay, so let's draw the line somewhere here. Okay, so in this situation, this x value right here is k. This value right here is k. Okay, and this line is the line x equals k. All right, so we have two regions. Let me color code them for you. This region is, I'm going to call this is region 1. Okay, this is region 1, and this region right here is region 2. All right, so guess what? The area in region 1 is 3 times the area in region 2. All right, so how do we use the language of calculus to express the area under the curve for region 1? All right, let's go ahead and do that. So for region 1, let's see, it's going to be the integral from negative pi over 2, the lower bound to the upper bound, which is k, of the function cosine x dx. Okay, that's for region 1. And then for region 2, um, the area is going to be the integral, starting from the lower bound is now k, because we're going from k to pi over 2 to pi over 2 of cosine x dx. Okay? All right. Well, what do we know? We know that this region is 3 times this region, right? So we need to triple region 2 to get 1. So basically, what I'm saying in essence is 3 times region 2 will yield region 1. Okay? Because that's what the problem says, right? The area from the left is 3 times that of the right. Okay, so let's see if we can set up an equation using this information and solve for x. Okay, so we're going to have the integral. 3 times region 2 is going to be 3 times the integral from k to pi over 2 of cosine x dx equals the integral from negative pi over 2 to k of cosine x dx. Okay? All right, so this just basically says that the area on the left, on the right is 3 times, I mean, is a third of the area on the left, or the area on the left is 3 times the area on the right. All right, so what we're going to do, we're going to use FTC part 2 to evaluate this integrals, this definite integrals. We're going to have a resultant equation, solve for k, and that will be our answer. Okay? All right, so let's go ahead and integrate this. Find this definite integral. The antiderivative of cosine, that's negative sine, so we have negative sine x evaluated from k to pi over 2. And then on the right side, we integrate in exactly the same function. Antiderivative of cosine is negative sine x, evaluated from negative pi over 2 to k. Okay? All right. Now let's focus on the left side, see what that is, and then we'll shift our attention to the right side. All right, so using FTC part 2, this is basically 3 times negative sine pi over 2, right, minus sine, actually it's minus negative sine. Gotta be careful there. Minus, I should have factored out the minus. That would have made my life much easier. So minus negative sine k. Okay, and then close that. All right, simplify further. This is going to be 3 times sine of pi over 2. If you remember your sine function, sine of pi over 2 is 1, so it's going to be negative 1 minus minus plus sine k equals, all right, and on the right side here, let's be smart and take out the minus. I'm going to go here. So on the right side, I'm going to take out the minus, plug in the upper limit of integration, which is sine k, all right, minus sine of negative pi over 2. All right, okay, let's simplify that. So that is going to give us negative sine k. Sine of negative pi over 2 is negative 1. Remember, your sine function goes like this, and that's negative pi over 2, so it's going to be negative 1. So minus 1, because you had a minus in front here before, like that. All right, let's simplify this side. Distribute the 3. You have negative 3 plus 3 sine k equals, distribute a negative here. These two are minuses, so they times to become a plus. So you're going to have negative sine k minus 1. Okay? All right, now we have an equation that I was talking about earlier. We got to solve this equation for k, and that will basically tell us how to partition it so that the area on the left is 3 times the area on the right. All right? So what I'm going to do is basically add sine k to both sides and add 3 to both sides. So we have all the variables on one side and the numbers on the other side. Okay, basic algebra. So we're gonna have let's add sign k here too. Add sign k. Okay. So these ones add out, cancel out. So we're gonna have 4 sine k equals minus 1 plus 3, 2. Divide both sides by 4. You have sine k equals 2 over 4, which is 1/2. Okay? All right, k is the inverse sine of 1/2. Take the inverse sine of both sides, so isolate k. So if you're between 0 and between 0 and pi over 2, the inverse sine of 1/2 is pi over 6. Okay, this is basically quadrant 1. So if you take the inverse sine of 1/2 in quadrant 1, it's going to be pi over 6 for 30 degrees. Okay, so there goes the k value that allows us to partition the space in such a way that the criteria is met. So this value right here, this k, is actually pi over 6. All right, pi over 6. So the answer is C. All right, let's move along to the next one. Question 14. It says if the function f is defined by f of x equals x to the fifth minus 1, then the f to negative 1, the inverse of the function f, is defined by. So this is a pre-calc process of finding the inverse. So if you're inverting, your input becomes your output, and your output becomes your input. And you solve the resulting switched equation for your new output, and that will be your inverse, okay? So for symbolic convenience, I'm going to replace my f of x with y. Remember, y equals f of x. It's easier to switch it this way. So y equals x to the fifth minus 1. And remember, when you're taking the inverse, xy, the inverse becomes yx, right? So what I'm going to do here is I'm going to switch the x and the y's, all right? That's how you find the inverse. So you're going to have x equals y to the fifth minus 1. All right, let's solve this for y. Add 1 to both sides. You have y to the fifth equals x plus 1. And the inverse of the fifth power is the fifth root. So we take the fifth root of both sides, a fifth root of y to the fifth, and the fifth root of x plus 1. Okay? All right, so this one cancels out with that since you're inverse operations, and you have y equals the fifth root of x plus 1. And guess what? This is the inverse of the original function. F inverse of x is equal to the fifth root of x plus 1. Okay? So the answer to question number 14, let's see, is option letter E. So there you have it. All right, let's move along to the last question, question number 15. It says if f prime of x and g prime of x exists, and f prime of x is greater than g prime of x for all real x, then the graph of y equals f of x and the graph of y equals g of x is what? Does it intersect only once, intersect more than once, does not intersect, could intersect more than once, or have a common tangent at each point of intersection. So we don't know which is bigger here. So what we're going to do is we're going to consider all cases, okay? Now, these two functions could either be increasing or decreasing, but we're going to focus on increasing. And if you reflect that situation, you get, you can understand, if you invert the situation, you get the decreasing case, okay? All right, so working with increasing should be sufficient. Now, so if f prime of x is greater than g prime of x, what does that mean? So if f prime, the slope of f of x, is greater than g prime of x for all x's, this means then that f of x is goes faster than g of x. Okay, f of x is going faster. That's what this means. All right. Whichever one has a bigger slope is like you're driving two cars. This is going at 15 miles per hour. This is going at 30 miles per hour. This one is this one's going faster. That's basically what it means. All right. Okay. Now that we've interpreted what this means, now we're going to consider three cases. Okay. Case 1. Case 1, how about we have f of x starting behind g of x. Okay, they're both racing, but g of x has a head start. What's going to happen? Um, so let me give you a sketch of the situation so you can understand what's going on here. So if f of x is less than g of x, let's say they're starting on the y-axis. So let's put f of x in red. So let's say f of x starts from here, and g of x started from a higher point. Let's put it in blue. All right. But since f of x is has its greater slope than g of x, it's going to be growing at a quicker rate, which means it's going to go up quicker. So if f of x goes something like this, guess what? G of x is going to be going something like that. All right. So there, at a particular point, f of x is definitely going to catch up with g of x, right? Because g of x is going so slowly. So in this case, we have one intersection. All right. Okay. Case 2. What if they both start on the same starting point? Okay, they both start on the same starting point. What are we going to have? What will the intersections look like? Okay. So f of x starts from here, and g of x also start from there. So I should have color coded my functions. So f of x is going really quickly as indicated up here, like this. That's f of x. And guess what? G of x is really slow, so it's going really slowly, like that. How many intersections do they have? They have exactly one intersection, which is the starting point, okay? And then after that, is g of x going to ever be able to catch up with f of x? Absolutely not, because the slope is, this one is always driving slower than the faster one, f of x, so there's no way it's ever going to catch up, okay? So this was g of x, and then f of x basically caught up and surpassed g of x, okay? All right, now the last case, guess what that is? The last case is, what if the faster growing function was given a head start? What if g of f of x was in fact greater than g of x? What do you see happening in that case? All right, let's consider the situation. So let's do the opposite of what happened up here. We have g of x starting beneath f of x. Okay? And as we know, f of x is very fast, so it goes up really quickly. But what happens with g of x? G of x is going slowly. Okay, you see towards infinity, you see how they diverge, and guess what? This divergence keeps getting bigger and bigger, right? So how many intersections do we have here? This function is going quicker, and it has a head start. Will g of x that's going slower, will it ever catch up? Absolutely not. So you have no intersection here. No intersection. All right, so what can we conclude here? Intersect exactly once? No. If f of x has a head start, then there are no intersections. Intersect no more than once. This sounds reasonable. It could be one or less. Do not intersect is false. Could intersect more than once? Absolutely not. Have a common tangent at each point of intersection. There's no way we can make that conclusion. Okay. All right. So the answer is clearly option B. It intersects at a maximum of one time if g of x started ahead of f of x. Or they started at a common point, or else there will be no intersection. Okay? So the answer to this is option B. All right, so thanks so much for taking the time to watch this presentation. Feel free to subscribe to my channel by clicking up here. And if you like this video, you can always click like. And please, please, please post a comment to let me know what you think about this clip. More videos can be found on math.com. Thanks again, and have a wonderful day.